In this video, we're going to look at some applications of rational functions. So the first example we're going to look at here is looking at the daily cost of manufacturing bicycles. So we have this function c of x that is equal to 80x plus 5,000. So our c of x is the cost of manufacturing bicycles in dollars, and x is the number of bicycles. All right, so then it tells us the average daily cost of manufacturing bicycles is that cost function divided by x. Okay, so part A, we just want to use our function in order to calculate the average daily cost for different numbers of bicycles. So we want to find the average daily cost of manufacturing both 100 bicycles and 500 bicycles. So let's start first with just 100 bicycles. So we're just looking for the average cost of manufacturing 100 bicycles. So we're just going to plug 100 into our function. So 80 times 100 plus 5,000 all over 100. Okay, and then we just need to plug that into our calculator. And if we do, we will come out with $130 as our average daily cost of manufacturing 100 bicycles. Okay, so then we can just do the same thing with 500 bicycles. So the average cost of manufacturing 500 bicycles, just plug 500 into that function. So 80 times 500 plus 5,000 all over 500. And again, just plug that into your calculator and you are going to get $90 as your average daily cost. So it's actually less per bicycle to produce 500 bicycles as it is compared to produce 100 bicycles. Okay. All right, so then part B asks us to find and interpret the horizontal asymptote. Okay. All right, so remember, in order to find the horizontal asymptote, we start by looking at the degrees in the numerator and the denominator. So if we look at this one, the numerator has a degree of 1, and the denominator also has a degree of 1. So same degree in the numerator and denominator. So remember then, if we find that we have the same degree in the numerator and denominator, then what we do to find our horizontal asymptote is we divide the leading coefficients. So in this case, we would have 80 divided by 1, or just y equals 80 as our horizontal asymptote. Okay, now we need to interpret it. Remember, that just means we're just going to explain what this means in the context of this example. Well, if you think about what a horizontal asymptote is, remember, if you have some kind of rational function and you have a horizontal asymptote, then that's telling us where our graph is leveling off to as you go toward positive and negative infinity. So this is essentially saying as we go out toward positive infinity, in the case of bicycles, we wouldn't go toward negative infinity. That doesn't make sense. But as x gets really, really big, our average daily cost, or our y, is eventually going to level off to about 80. So a way that we could say that essentially is as the number of bicycles manufactured. Now, I'm not going to say goes to infinity because realistically, we're never going to get large enough to consider it infinity for any kind of real life application. So I'll just say as the number of bikes manufacturers increases or gets really big, you could say, the average daily cost will decrease and begin to level off around $80. Okay, now we can sort of prove this to ourselves if we plug in another number. So we can already see that trend happening just by looking at the 100 bicycles and the 500 bicycles, right? We saw that if you manufactured more bicycles, then it cost less money to produce those bicycles. So let's just say, oops, plug in another number. Scooch that up. Right, it didn't ask us to do this, but let's just say we wanted to find the cost of producing 1,000 bicycles, just to kind of see this horizontal asymptote at work here. So if you plugged in 1,000 for your x value in that average cost function, let me just plug this into my calculator. Okay, now we have an average cost of $85. So again, we can see that that average cost is decreasing and getting closer to that $80 value. That is our horizontal asymptote. And you would see this trend continue. So the bigger this X value gets in here, the larger that number of bicycles is that you're manufacturing, the closer that average daily cost is going to get to your $80 asymptote. All right. Let's go ahead and take a look at another example. So example 2 says the Game Commission introduces 100 deer into newly acquired state game lands. So the population N of a herd is given by this function. N is equal to 25 times the quantity 4 plus 2t all over the quantity 1 plus 0.02t, where t is the time in years. So we're measuring the population N of a herd as a function of time t in years. So part A just says find the population when 5 years, 10 years, or 25 years have passed. So again, this just means take the 5, 10, 25 and plug it into t in our function. Okay. All right, so if we do that, let's start with 5. So our n, you'd have 25 times 4 plus 2 times 5, all over the quantity 1 plus 0.02 times 5. Okay, and if we plug that into our calculator, we get a decimal, but it's approximately 318. And remember, n is measuring the size of the herd, and these were deer that we were talking about. So this is approximately 318 deer. Okay, so if you do get a decimal for any of these, you definitely want to round it to the nearest whole number because it doesn't make sense to have part of a deer, right? So just round it up or down to that nearest whole number. Okay. All right, so then we can also plug in 10 years. So if we plug in 10, 25 times 4 plus 2 times 10, all over the quantity 1 plus 0.02 times 10. And again, if we plug this into our calculator, we would get now 500 deer. Okay, so we can see that the number of deer that are on these game lands is increasing over time, right? We start with 100 deer. After 5 years, we had 318 deer. After 10 years, we had 500 deer. And then after 25 years, let's see what happens when we plug a 25 in. So 25 times 4 plus 2 times 25 divided by 1 plus 0.02 times 25. Okay, and if we plug that into our calculator, we're going to get 900 deer. So again, we see this trend continuing, that as the number of years increases, the number of deer that are on these state game lands is increasing as well. Okay, now we're going to continue to see this trend that as time passes, we're going to have more and more deer. But if we think about this logically, the number of deer just can't increase forever. At a certain point, you're going to reach, a capacity limit. There's only so many deer that can physically fit in these lands, but also there's going to be a limitation to how much food they can eat, how much water is available, and that sort of thing. So at some point, we could probably expect that this deer population is going to level off. And that's what our horizontal asymptote would tell us. Okay, so in part B, we want to again find and interpret the horizontal asymptote. Now, what I would do on this one, if we're looking at our function here, we have that 25 factored out of the numerator. So the first thing I would do is just go ahead and distribute that 25 in. So we'd have 100 plus 50t all over the quantity 1 plus 0.02t. Okay, it's easier to figure out a horizontal asymptote if everything's just fully expanded, because then it's easier to identify our degree and our leading coefficient. So like we talked about on the previous example, for a horizontal asymptote, we start by looking at the degree of the numerator and denominator. And again, we can see on this one that both the top and the bottom have a degree of 1, in which case we just divide our leading coefficients. So the leading coefficient on top is 50, the leading coefficient on the bottom is 0.02, and if you divide that, 50 divided by 0.02, we come out with a horizontal asymptote, so 50 over 0.02. Let's write this down. Okay, so we come out with an asymptote of 2500. Okay. All right, now again, that horizontal asymptote is basically where our function is leveling off as our x values get really, really big. So in this case, our x values are representing the time in years. So as the number of years increases, or as time passes, that deer population is going to continue to increase, but eventually start to level off around 2,500 deer. So that's sort of the maximum capacity, if you will, of deer that you can actually physically hold on this island. Okay, so as time passes, the deer population will increase and begin to level off around 2,500. Okay, all right. Okay, so lastly, example 3. This time we are looking at the population in the United States. So it says a model of the population, P, in millions of the United States from 1960 to 2009 is given by this function. P is equal to 2.6174t plus 176.112, where t represents the year since 1960. Okay, so it says a model for the land area A in millions of acres of the United States from 1960 to 2009, so that same time period, is given by A is equal to 2,263.960. Okay, all right, so part A says construct a rational function for per capita land area, L. Okay, in acres per person. Okay, so acres per person. Remember, anytime you see that word per, that's basically telling you in your fraction, that's where you're going to put your division symbol. Okay, so per means divide, essentially. So if we are looking for the per capita land area in acres per person, that means we're trying to construct a rational function. We want acres on top divided by the number of people. Well, those are exactly the two functions we were given, right? We were given our function A, which was measuring the land area in millions of acres in the United States, and we were given our function P, which is measuring the population or the number of people in the United States. So our function L of T is just going to be taking A divided by P. All right, so our A function was 2,263.960, and we're going to divide that by our P function, which was 2.6174t plus 176.112. 0.112. Okay, so that function is representing the per capita land area in the United States from the years 1960 to 2009. Okay. All right, so again, part B asks us to find and interpret the horizontal asymptote again. So this time, if we're looking for our horizontal asymptote, we again start by thinking about the degrees in the numerator and denominator. Well, the denominator has a degree of 1, but the numerator, since there is no t value in the numerator, has a degree of 0, meaning we have a smaller degree in the numerator than we have in the denominator, which anytime the degree of the numerator is smaller, that automatically puts our horizontal asymptote at y equals 0. Okay. So remember that horizontal asymptote, when you're thinking about any kind of application function, this is essentially telling us where our y value is going to level off to as our x value increases. Okay, in this case, our x value or our t value, if you want to be more precise, is representing um, the time in years from 1960 to 2009. So as time passes, our y value, or our L value, in this case, the land area per capita, is going to slowly decrease and approach 0. Okay, now obviously it's never going to reach 0 because a horizontal asymptote does never actually hit that value, but it just slowly approaches that value over time. Okay, so here we are saying as time passes, or as the number of years increases, however you want to word that, since 1960, the per capita land area will decrease and start to approach 0. Okay. Now again, it's never actually going to get to 0. Okay, that's the whole thing with an asymptote, is it tells us theoretically at infinity, this is what our function is going to equal. But of course, realistically, we never actually get to infinity. So just slowly over time, the per capita land area is going to increase, or excuse me, is going to decrease and get closer and closer and closer to 0 as time goes on.